Dear student, this is going to be our lecture 5 in the course MTH 803, and in the previous lecture we had reached this point in the proof of our theorem. From this it would imply, now using the fact that the previous theorem 0 to a fx sine nx by x dx is equal to f of 0 plus 0 to infinity sine x by x dx, applying it, taking a to be our, because a could be any positive number, we take it to be pi by 2 in this case. And here noting that if we change t to minus t, it doesn't affect this part of the integrand, so I can safely write that this should be basically f of 0 minus plus f of 0 plus, using the previous theorem and taking this out, this would be 0 to infinity sine x sine t by t dt. And if you replace this by pi by 2, this would be just the average of these two values, so you would get this divided by 2. So this is what we had to prove. We actually had to prove this much, but this should give us something to ponder upon, that if we just take the series of the Fourier cosine coefficients, then this would be just the average of the values around 0, the limiting values around 0, unka average. Okay, this finishes the theorem that we were doing, and now let's move further to our next thing, that is the Dirichlet's conditions, or the Dirichlet's criterion for the sufficient conditions for the convergence of a Fourier series. Now that's going to be our next thing, now which will finish some part of our first unit, not all, but important part. Okay, my camera has been okay. Now let me write down, this is going to be our Dirichlet's criterion, and we are going to use, of course, as mathematicians do, our previous knowledge that we accumulated over the past few theorems. Now, for sufficient conditions for the convergence of Fourier series, of course I mean pointwise convergence. But there is also criterions for uniform convergence and all that, but we are not going to go there. That would take us a little too far, and because our course is very basic, very elementary. Okay, our theorem, this main theorem would be if f is a function, it is bounded, you just look at the notes also, bounded, periodic, with of course period 2 pi, that's what we have been assuming throughout, and of course integrable, the big integrable, minus pi to pi, and another condition, piecewise monotonic, means that you can divide this interval into finitely many subintervals such that over each of that subinterval this function is monotonic. Monotonic increasing or monotonic decreasing, no issues. If it is piecewise monotonic and periodic in this interval and of course integrable, then its Fourier series, that is summation 1 by 2 n naught plus summation n runs from 1 to infinity a n cos nx plus bn sin nx, that is the Fourier series of this function, would be just the average of its limiting values at x, that is 1 by 2 f of x minus plus f of x plus for all x lying between minus pi and pi, the open interval, right? And it would be just the average of f of pi minus plus f of minus pi plus for of course x equal to plus minus pi at the endpoints. Now you have to remember our notation. What do I mean by f of x minus? Would be limit x approaches, limit t approaches, let me write t, limit t approaches to x from left f of t, just a shorthand for this, and it is the value is approaching x from left. And similarly when I say limit f of x plus, same applies to minus f of pi minus, same idea. This would be limit some variable t approaching x from right, f of t. So getting this out of the way, you just note that if f is continuous at x, if f is continuous at x, f of x minus would be just f of x, and f of x plus would be again equal to f of x. So this would be f of x plus f of x divided by 1 by 2. So in case the function is continuous of x, indeed the Fourier series of the function fx would converge to fx at the point of continuity. But we are not assuming continuity, we are making it loose. We are just saying it would converge to this value. Of course, this value would be the same as fx in case the function is continuous at the point x. Of course, there is another theorem which would be for uniform convergence, the function has to be such that its derivative is also continuous. But we are not going to do that theorem. That's not a part of our course, but you can check. Okay. Now we are going to use, so you might have to look at the notes and our earlier theorem for the proof of this theorem, that we had written this 1 by 2a0. This is our proof. Again, this is just what we had done earlier. We just have to use it. Our Fourier series is like summation k runs from 1 to n ak cos kx plus pk. We just take the finite, the partial sum. We have to the finite sum. Of course, if this is the nth partial sum of the Fourier series, if this converges to some number, that means the Fourier series converges to that number. So we take its nth partial sum, and we know that we had written it as, you just look up in the previous lectures or the notes, that this is equal to minus pi to pi f of t dn of x minus t dt, where dn is the Dirichlet's kernel. We had done it earlier, which can be written as 1 by 2 pi. Again, we have done this earlier, minus pi to pi f of x plus t dn of t dt. And we also evaluated that dn at t or dn at x, whatever it is equal to sine of n plus 1 by 2t divided by sine t by 2. And this we have done. So that this means it is equal to 1 by 2 pi minus pi to pi f of x plus t, is making the substitution for d and t. It is sine of n plus 1 by 2t divided by sine of t by 2 dt. Right, we just again break it up into 2, so it would be 1 by 2 pi minus pi to 0. The integrand would be same, let me not write it. Then 0 to 2 pi, the same thing. Of course, it is x plus t. Okay. Then after that, this can be written as, by making the substitution t equal to 2u, and again first we change t to minus t. So if I change t to minus t, it would be, as we did it earlier, 1 by 2 pi, and using the fact that the change t to minus t doesn't change anything here, so it would be, the first integral would be 0 to pi f of x minus t sine of n plus 1 by 2 t sine t by 2 dt. And of course, here I just keep the same, 0 to pi, whatever it is, right? Then we put x, as we had done in a previous theorem. I put x equal to 2u. No, sorry, my change of my integral. What I'm saying is my variable of integration is t, so I put t equal to 2u, and I would get 2 divided by 2 pi from 0 to pi by 2 f of x minus 2u, and here I would have sine of n plus, sorry, it should be 2, so it would be 2n plus 1 into u divided by sine u du plus 0 to pi by 2. It is the same substitution that we did in the earlier theorem, so it shouldn't be difficult. 2n plus 1 sine of u du. And of course, now we have oh, of course, here I have got, just don't miss it, it is f of x plus 2u. Okay, okay, good. Now you just take the, let n approach infinity, and we know what happens to these integrals as n approaches infinity. What was that theorem जो हमने किया था वो ये था. We know what happens limit n approaches infinity 0 to infinity fx sine nx by x is the same thing as limit n so not this one, the earlier one. Okay, we had done this theorem. I just have to find it out because if you look back at your results, we evaluated it to be this thing. Is it the same? I've got sine by x. Oh, what was the theorem? What is that result? Okay, let me check from the notes. As n approaches infinity, okay. As n approaches infinity, we have done this. Oh, I want another page. Okay. Now we have done this. If you look at your notes or your previous lecture, we have done this limit n approaches infinity for an integrable function f of x sine nx by x sine x dx is the same thing as limit n approaches infinity 0 to sorry, here I have to put this thing as 0 to a. Okay, we have proved this thing. Limit n approaches infinity 0 to a, where a is some positive number, phi x, so that you don't get a little confused, although there is no reason for confusion. I can replace phi by f. It's the same thing as limit n approaches infinity integral 0 to a phi x times sine of nx divided by x dx. Okay, so applying this theorem and thinking of f as phi, what do you get? Now this thing on this next page should be equal to 1 by pi, right? 2. This can be replaced. Then if I let n approaches infinity, my left hand side would become 1 by a naught plus summation n runs from 1 to infinity, the Fourier series. Okay, let me not write the left hand side, let me first find out the right hand side. Okay, as n approaches infinity, this should be the same thing as 0 to, of course, limit n approaches infinity 0 to pi by 2 f of x minus 2u sine of n to n plus 1 divided by sine of u du plus limit n approaches infinity 0 to pi by 2 f of x plus 2u sine of 2n plus 1 times u divided by sine of u du. Compare it with the above equation and think of phi x as f. This would be 1 by pi limit n approaches infinity 0 to pi by 2 f of x minus 2u. This would be sine of let me write it as 2n plus 1 times u divided by u du plus, of course, the same thing, limit n approaches infinity 0 to 2u, 0 to pi by 2 f of x plus 2u sine of 2n plus 1 u divided by u du. Now you know that we have done it, it's written so many times. Okay, now again we know something else, the theorem that we did after that. We also know, let me put it inside this circle, we have also showed that limit n approaches infinity 0 to a fx sine nx by x dx is equal to f of 0 plus 0 to infinity sine x by x dx, and if I use that, this is equal to pi by 2. This would be f of 0 plus into pi by 2, because this integral is convergent and converges to pi by 2. Now look at this. I have here psi f of x minus 2u, and you have to remember here the variable of integration is u, right? Right. So if I make some change in variables, and remembering that changing u to minus u doesn't affect this integral, because minus would be out and it would just be cancelled out. If I take all these considerations, then this would be nothing but 1 by pi integral limit n approaches infinity. Oh, I can just do away with the infinity. This would be just f of x minus into pi by 2 plus f of x plus into pi by 2, x plus, right? So just take pi out, so it would be just f of x minus plus f of x plus divided by 2. And remember that now here it's in the case of theorem I have got f of 0 plus, but then the variable of integration is x, right? So this is basically limit x approaches 0, limit x approaches 0 from right f of x, this thing here, right? Now if I for the time being put x minus 2u equal to some t for the time being, and take u to be greater than 0, we know that, what do we know? That limit okay, limit what is the function f of t as t approaches, I put this equal to t from 0 to right, would be the same thing as the limit as x approaches to 0 from left f of x. You just check this, which is equal to f of x minus. So that means this is valid, and same applies here, right? Just a evaluation of limits, making some substitution. So that finishes our Trickle's criterion. And of course, yeah, I missed something. That is in the case endpoints. And endpoints, there is no issue because the function is periodic. The function is periodic, so since so let me write it down like this. Because function repeats itself after every 2 pi intervals, so I've got a minus pi here, so pi here, so I am repeating it. That means here on the pi I would repeat again the same thing. The function would be like this, then the function would be like this, it would be repeated. So when I am evaluating the average value from here and here, it would be the same thing as average value from here and here. I hope you get it, right? You approach pi from left, and minus pi from right is the same thing as approaching pi from left and right, because the function is periodic. So that means in the case of endpoints, f of what was it? Okay, we have got this the limit in the case of any point inside, right? So but in the case here, this limit, and in the case of pi, okay, keep it as it is, f minus, we are approaching this pi from left, so you can write it as f of pi minus, that's okay, but this pi plus is the same thing as minus pi from right. And a limit here, limit here is the same thing as limit here. Approaching minus pi from right is the same thing as approaching pi from right, because of the periodicity of the function. Okay, that finishes our Trickle's criterion for the pointwise convergence of the Fourier series. Okay, let me conclude it here. Thank you.